Good afternoon and welcome to Vector Institute's Research and Careers in AI. Today's session shines a spotlight on some of the wayfinders in artificial intelligence, with companies that have driven significant advances in AI and have captured our imaginations along the way. My name is Melissa Judd, and on behalf of everyone at Vector, thank you for spending this time with us, and a special thank you to our presenters, Google, NVIDIA, Thomson Reuters, and Uber ATG for sharing some of their work. I would also like to acknowledge and thank our funders, the Province of Ontario, the Government of Canada through the Pan-Canadian AI Strategy administered by CFAR, and industry sponsors from across the Canadian economy, including the 4 companies presenting here today. I also wanted to pause to acknowledge the land on which Vector is located here in Toronto, what is now a meeting place for many First Nations, Métis, and Inuit peoples, as well as newcomers to Canada from around the globe. The land we are situated on is the traditional territory of many nations, the Mississaugas of the New Credit, the Anishinaabe, the Chippewa, the Haudenosaunee, and the Wendat peoples. We acknowledge that Toronto is covered by Treaty 13, signed by the Mississaugas of the New Credit, and the Williams Treaty signed with multiple Mississaugas and Chippewa bands. We are grateful for being hosted on this land. Now, before I introduce our first speaker, I did want to remind everyone that today's session is being recorded, and there is an opportunity to ask questions of our speakers at the conclusion of our 4 talks. In the meantime, though, feel free to queue up your questions in the Q&A function at the bottom of the screen with your question. And of course, if it's directed at a specific panelist, please remember to include their name. I would now like to introduce our second speaker, Donny Cheung, whose talk today focuses on perspectives on AI enablement in healthcare. Donny is the engineering lead for healthcare AI with the Google Cloud Healthcare and Life Sciences Group and works on building products that leverage cloud technology to apply advanced analytics and ML to healthcare data problems. Previously, he worked at Google's display ad team, building global scale ML applications to improve the quality and relevance of our display ad experiences. Prior to Google, he worked as a senior scientist at a medical device startup in Toronto, focusing on medical imaging, device design, and image reconstruction algorithms. Donny holds a PhD in mathematics from the University of Waterloo. Welcome, Donny.
Thank you so much. Right, so what I'd like to talk about today is a little bit of a reflection over the years that I've worked in healthcare AI at Google on why it is that we don't see more artificial intelligence applications in the healthcare industry today. And one of the pieces of evidence that you can see that the adoption is not as high as it ought to be is that every time somebody comes up with a new breakthrough or somebody comes up with a new application for artificial intelligence in a healthcare domain, they write a press release about it. And I would love to be able to get to the point where this type of technology is so ubiquitous that we don't feel the need to write a press release every time we do something new, that every time we have a new model that predicts something out of chest x-rays or something like that, that it isn't worthy of some sort of announcement. So what I'm going to talk about today specifically is 3 questions. One, how has data been used in healthcare in the past? Just sort of a quick overview. 2, what are some of the challenges that are facing data-driven approaches to medicine today, which sort of speaks to the topic. And then hopefully a little bit of forward-looking optimism about what are some of the key technologies that I think will unlock the promise of data-driven, machine learning-driven medicine in the future. So first of all, a little bit of history. So algorithms, I mean, everyone here knows how important they are to our daily modern lives and how the potential for new data-driven algorithms to unlock a lot of applications in medicine just sort of holds a lot of promise out there. For reference, this is actually a picture of the very first phone book, 1878. That's almost 150 years ago. This here is actually a fairly historic text. In 1761, a person by the name of Morgagni, he actually produced the first data-driven effort to identify the causes of diseases using actual cases. So he basically spent a lifetime collecting detailed information about every case that he ever saw, and then more to that, he organized it by basically anatomical location, right? So this is became actually the very first index of, you have symptoms and you'd like to understand those symptoms and you'd like to try to figure out what disease you have. You look it up in this book and you figure out like all these other cases which are similar to yours. Morgagni is sometimes recognized as one of the founders of modern science-based medicine because of the work that he did here. Fast forward about a century, this is a famous map made by an epidemiologist, John Snow. Actually, epidemiology didn't exist then, but he sort of invented modern public health and epidemiology. He famously used this data visualization to identify the source of a cholera outbreak in London. It turns out that it's somewhere in that middle region where the black bars are the highest. It turns out to be a water pump, which was the source of a cholera outbreak. People didn't understand that dirty water could cause cholera back then, so this was actually a significant breakthrough. And then another interesting point in history, 1890 is when the first time that we used a machine to tabulate health data as part of the first US Census. And if you're ever curious, there's like a hugely fascinating story about the first US machine tabulate, the 1890 census, how they realized that they could not do this by hand. They had this competition to find a way to mechanically tabulate the census. But interestingly, because this is also the first census where health-related questions were asked, this becomes the first machine-tabulated population health data set. And to that point, you could actually, quote unquote, write queries against this database, which basically you submitted requests into the people that ran the machine, and they would actually use the punch cards and run queries for you if you wanted to understand these questions with respect to a certain population in a county or in a state or something like that. You could actually ask them to retabulate the data with your query in mind. So the point here that I wanted to make is that data science in medicine is actually very old. It's hundreds of years old. We've been thinking about how to leverage data in data science in healthcare for a very long time. But it's only in recent decades where we've really pushed forward on that technological aspect, where algorithmic developments have gotten to the point where we can think about this AI-enabled healthcare future. So in order to succeed at a deployment of machine learning in any healthcare scenario, it's very similar to any machine learning deployment. You need basically three things. You need clean, unbiased feature data. You need enough of it so that you can train a model that has good predictive value. You need these advanced techniques, right? You basically have to use deep learning nowadays if you want to do the really, really cool stuff. And then you need a way to deploy it, right? You need the right outputs, the right insights from this data delivered to the right place within that healthcare workflow, to the point of care, right? If you deliver great predictions about disease prevalence or something like that, but it doesn't fit into the normal workflow of an attending physician who is looking at you, right? Like if you're just doing this after the fact, or if you have a system which will send you a letter 3 months after the fact that you may or may not have this disease, that becomes much, much less relevant. Okay? And I mean, each of these problems you can write an entire talk about, right? You can talk about for hours and hours and hours, but we don't have that. So I wanted to touch on what I think are 4 up and coming technologies that speak to these 3 main problems. And these 4 key technologies are large-scale data warehousing and analytics, basically just scalable compute, sensor networks and personal computing, taking compute and measurement to the patient, machine intelligence, clearly that whole area of study, and then public cloud computing, which I think more and more in the future will become a part of that healthcare data science story, being that one of the main blockers to deployment and to really like real world applications of healthcare machine learning are that a lot of the data that needs to be used in order to build these types of models and applications are still locked away in these silos where small amounts of data are held in small collections in many, many places. And it's almost impossible for anyone to come in and say, like, I would like to train a new model that really broadly looks at this problem, looks at it for a large population, has enough data to understand the biases and help mitigate those, and can be deployed at scale. That is really, really hard to do nowadays, without these technologies. So, just a quick word about, sort of where I see sensors in personal devices. Personal devices, especially things that are already attached to your cell phone, they allow patients to actually contribute quality data. One of the issues nowadays is that in most medical applications, they're only able to collect data when you go into the clinic, right? So for medical imaging, this is okay. Like you go in and get a chest X-ray, there's tons of data there. But if you're looking at something simple like blood pressure, and you want to track someone's blood pressure over time, and you're only going into the doctor's office every, say, half year or so, and they measure your blood pressure and your heart rate and stuff like that, you've now got a time series on the order of like maybe every 6 months, or if you're lucky or unlucky, maybe every month or 2 weeks, 2-3 weeks or so. That doesn't really help, right? That doesn't, that you can find like sort of long-term trends there, but to be really zero in on places where blood pressure are an indicator of disease and things like that, you really need to be able to collect data much more frequently than that. And that starts with being able to empowering patients to collect data themselves and making sure that they're of sufficient quality that you can run inference over them. Data warehousing and analytics. I think just the amount of data that's coming out. I have this stat where every time I give a talk similar to this, I increase that number year over year. Right now, in 2019, the USA had 132 million CTs or MRI scans. These are 3D volumetric scans. In Canada, it's about 10% of that. I think I didn't write this down. I think it's about 12 or 13 million CT and MRI scans done in Canada in 2019. And just the volume of data that's being collected right now, precision medicine is a term that's being used a lot, where we sort of start adding genomic factors in and really trying to figure out at a personal level, what is it about a certain patient versus another patient that is causing a certain type of disease or disease response versus another. That volume of data needs to be managed. That volume of data needs to be processed in a way that is scalable. And so these technologies speak to that. And then machine intelligence, of course, all of these modern techniques that we're throwing at these difficult problems. I mean, I like talking about deep learning. We use a lot of deep learning on my team, but it requires a large amount of high quality training data. And especially in healthcare, data is very scarce, which I alluded to earlier. It is hard to find consistent, broad population-based healthcare data sets. And so what we have to do is we have to do our best with the limited data that we're able to license or acquire, and to hope that they're generalizable enough to be useful for a broader population. But you do run the risk of for example, having a lot of data from one part of the country, or even one country, being used to generate models that are being used to predict, disease or things like that for a population that could be very, very different. And that's something that you have to keep in mind as you build and deploy these types of technologies. One other blocker, or maybe this is a good thing, is that the regulatory framework across the world is not actually quite ready for a lot of AI type approaches. The way that most, and this is Health Canada, FDA, European Commission, a lot of their approaches right now are to treat AI type technologies the same way that they would treat any other medical device. That it's evidence-based. You run clinical trials, and you get data, and that data tells you whether or not this machine, quote unquote, this machine is safe. And for a lot of AI approaches, I mean, for some AI approaches, that's perfectly fine. You train a model and then you go and prove that this model is fine, and then you go deploy it, and then now you've got a machine. But if you really want to get at the places where AI gives you advantage over existing techniques, part of that is the ability to continuously improve that model as you receive data over time. And the regulatory story around that is very, very murky right now. How do you version a machine learning algorithm? What do you do? Like, how do you actually accurately calculate its performance and quality metrics? How do you account for the fact that technically the performance of the medical device can change over time and can change in a way that that might run counter to the clinical trial that you ran in order to get it approved in the first place. So that story isn't out there yet. And then even sort of further than that, there's techniques like reinforcement learning, for which the regulatory framework just does not have the equipment, doesn't even have the language to be able to regulate what it means for there to be, for example, a reinforcement learning approach to solving some sort of healthcare problem, where it isn't just like, I've got this data set and I can add things to that data set and I can version and model over time, but it's actually just like a back and forth approach between the data and the system. So those are challenges for AI deployment that I think need to get solved at many levels, not only the technological level, but also the regulatory level. And then public cloud computing, really just a way to decouple, de-silo data sources from each other, and to provide a basis for scalable compute power to be applied across these data sets. I think data management and getting all this stuff into the same place is going to be a huge factor in the future viability of AI type technologies in healthcare. So I wanted to sort of quickly run through some places where I think healthcare is heading in the future with these types of technologies. One of them is a transformation of hospitals as data hubs, information hubs, rather than just a place where sick people go to get treated. This is the future hospital would become a place where data curation becomes a key activity because of its value in patient care. I also think that precision programming, genomic, precision medicine, genomic data, inclusion of that, and integration of all of this data into a care delivery system is going to be a requirement of the hospital of the future. All of this stuff needs to come together in a rigorous and sustainable way. I think one mental model that I like to offer people in how to think about machine learning is that machine learning operates or can operate very much in the way that labs currently operate. That when you want blood work, a physician will collect something from you. They will take that, collect it, package it. They will send it off somewhere. And then something magical happens at that somewhere place, and then a whole bunch of data comes back, and then that data, you understand exactly how to use that data in the care of the patient, and you understand, and that data gets added to that patient's record and becomes a part of that patient's care experience, right? Very similarly, I think the right framework to think about how machine learning gets applied in medicine is to think of them like labs, that you collect data from a patient, you send that data off to a place, whether it's within the hospital or a third-party service. Some insight gets generated that you understand, and most importantly, that insight has a place to live within the care delivery of that patient. One caveat to that is a lot of people are concerned about things like explainability. I think a new understanding of explainability will have to come from the healthcare industry, where people will have to learn to be okay with the nature of decisions that are made by algorithms, mostly because they're not particularly different from the types of decisions that people make in terms of what's actually explainable versus what people are, retrospectively are able to to put forward as an explanation for why they made one decision or another. And then finally, I like to challenge the healthcare community to think about clinical data and maximizing patient benefit as a moral imperative rather than as a walled garden that they have to curate. That our default should be to find ways to securely and with respect to patient privacy share clinical data with researchers as much as possible, so that we can be giving more data into this ecosystem of research to build these algorithms and sort of benefit the community at large from these advances. And with that, thank you for your attention.
Thanks so much, Donny, for your insights on some of the key enablers and complexities of AI in healthcare. It is an incredibly complex domain. Just a quick reminder before I introduce our next speaker that we are doing a Q&A at the end of our talks. So please feel free to queue up any questions you have in the Q&A feature below.